it doesn't actually have a path, or it could have advertised a very high cost path going there. But then you'd have to do some additional stuff to make that work. So let's not go there. Okay. The third option, and actually this is probably the most common in the very large scale providers, is they'll run a separate appliance or device called a route reflector. Think of this as a special server, and the job of that server is it sets up IBGP sessions to all the border routers. So it sucks in all the routes advertised to any border router in its domain. It runs a computation to select paths, and it goes off and programs all the routers in your domain. Okay, this is called a route reflector. No, they exist. In this class, we're just assuming option 1, so make sure that option 1 is clear to you. Any questions? All right. So how is all of this actually implemented in terms of protocol messages and protocol exchanges? So the key here, again, the BGP protocol specification has quite a few message types. In this class, we're going to focus really on what we call a route update. But just again, know that there are many other types. For example, there's a type of message to open a session. There's another type of message called a keep alive, just to say this session is still active, this border router is still up, and so on. The one that we care about is what we call a route update type of message. This is a message that informs a border router either I have a new path to this destination prefix, or I have an update, maybe I've changed some of the path length or the actual path associated with this destination, or sometimes what we call a route withdrawal, which is a border router telling another border router, I no longer have a path to this prefix. Okay. So let's dig a little bit into what route updates look like. At the highest level, route updates are as simple as they get. I have a prefix, and I have a set of what we call attributes associated with that prefix. Okay. So the prefix is exactly what we've been talking about. It's a /16, a /24, whatever you want. It represents a whole host bunch of destination hosts aggregated into a prefix. The attributes are a general mechanism that we use to describe or express properties about routes. And as you're going to see, all of the secret sauce, all the smarts of BGP is kind of packed into these attributes. So you can think of them as they describe a route. One way mentally to think about it is it's a set of key-value pairs associated with a route, where the key is a particular attribute type, the value is the value of that attribute. And we're going to use those to implement policy and to do route selection and route export decisions. Again, some attributes are local to an AS, so there are some attributes that will be associated with a prefix or associated with a path that a border router will never share with border routers outside its domain or with any router outside its domain, so they're local. There are also attributes that are propagated in eBGP route advertisements, so there are attributes that will get propagated across the internet. And in general, there are many standardized attributes. We are going to talk about 4 important ones in this class. Okay? So first attribute, something we've discussed already, is this notion of an AS path. So if you remember from the last lecture, we said BGP is a path vector protocol. It actually, when you advertise a prefix, you enumerate the sequence of autonomous systems needed to reach that prefix, and this is how we prevent loops. So AS path is just that vector of ASs that you're traveling to get to that prefix. Okay? It's carried in route advertisements. So what it would look like is something like this. So let's say in this example, I have Princeton, and Princeton is AS88. It has a prefix 128.12, 112/16, and it's connected to AT&T. Okay? So the Princeton and AT&T are going to have an eBGP session between their border routers. And in that session, Princeton is going to advertise, this is my prefix. If I dig into what that advertisement looks like, and we're getting now a little bit into the syntax of these messages, what that message is going to say is, here's my prefix, 128.112, so on, and here is my AS path attribute. And my AS path attribute at this point just says AS88, because that's where the prefix is. That message is going to get propagated through IBGP and so on to this other router on the right, which is still in AT&T's domain. And now AT&T, let's say, is going to advertise that prefix further to Berkeley. if I go look at what that message being advertised between AT&T and Berkeley looks like, again, it has the IP prefix. It's the same prefix, unchanged. Now the AS path attribute says 701888. So you know that your path is you're going to through AT&T and then to Princeton. Okay. So pretty simple. AS path just records the vector of ASs needed to reach that destination prefix. The second attribute, any questions on AS path? It's pretty much doing what we said path vector would do. The second attribute is what we call local preference or local pref. This is actually where GAU-Rexford gets implemented, and all the routing follows money gets reflected in local pref. So the way local pref is used is to choose between different AS paths. Local preference is local to an AS, as the name suggests. It also makes sense because remember we said ASs don't like to publicize their policies about customers versus providers versus peers and so on. So local pref stays within a domain. That means it's carried only in IBGP sessions and IBGP messages. And in general, local preference, the higher the value, the more preferred it is. So it's quite intuitive. Let's go back to our example here. And now in this case, we have Princeton again, AS88 up there. And I've complicated the picture a little bit in that Princeton now reaches AT&T potentially through AS100 or through AS200. Okay, it has a path. So AT&T can reach Princeton either through AS100 or AS200. The way we're going to use local preference is that let's say AT&T prefers using the path through AS100 because maybe 100 is a customer and 200 is a peer. Just to reflect GAU-Rexford. So what AT&T is going to configure its border routers to do is it's going to say at that border router, when you get a prefix advertised by AS100, add to that path, internally when you store that path, add a local pref value of, let's say, 300. The value doesn't matter. I'm just picking it out of nowhere. And so now if you looked at the routing table within that border router, you'd see a path that says something like, for this destination prefix, your AS path is 180, and then followed by 88. And this route has a local pref of 300. You would likewise configure on the other end, you don't like AS200 as much, so you would do the same configuration, but you would say, I'm going to give it a local pref value of 100. Okay, so it's lower preference. And now IBGP is going to share those entries with all the other routers in the domain. And so now what is any router going to do? In order to implement GAU-Rexford, the only thing sort of mechanistically that a router has to do is say, I'm going to pick a path to that prefix. I have two options for how to get to that prefix. I'm going to pick the one with the higher local pref. So I'm going to go through 100. Okay. Any questions on this? Yeah. Yeah, today manually often. So the operator knows what kind of relationships they have with AS100 versus AS200. So they configure their routers to say local pref coming from this AS is 300, coming from that AS is 100, which should cause you some discomfort. Any other questions? Does this fully implement GAU-Rexford? So GAU-Rexford said, customer better than peer. So assuming 100 is a customer and 200 is a peer. What happens if AS100 goes down or it withdraws the route? You'd need to update the table and you'd take out 300, the first entry, but you would use your path going through 200. Right? So it's doing the right thing. It's prioritizing. It's not eliminating routes. How would you actually, I think your question is, how would you actually know to get rid of that route? So this is where a route update that's a withdrawal would come in. So AS100, either you time out the route and then the border router would withdraw it, or AS100 might explicitly withdraw the route. Any other questions? Okay, so let's actually move on to a slightly more complicated case now. And as you'll see, the BGP, conceptually, the approach is simple, and what we're trying to do is very intuitive. Implementing it in a distributed fashion, given the realities of how ASs interconnect, is where things get a little tricky. So this is the same not the same example as before, because so far we've been assuming there's one link between two ASs. In reality, what is very common is that two autonomous systems, especially large ones, will have connections between them at multiple places. So if you're AT&T and Verizon, you probably have connections between the two networks on the East Coast, in Chicago, on the West Coast, in Europe, in Asia. So you have multiple of these connections between two different ASs. Okay? And so now when you think about going back to this Princeton to Berkeley path, you kind of have two paths, right? Either you can go through something like, let's say, the orange level router path, or you could go through this green path here. So notice this is the same AS level path. I'm going Princeton, Verizon, AT&T, Berkeley. So at the AS level, it's the same path. At the router level, it's a pretty different path, right? In one case, you're switching from AT&T to Verizon on the West Coast, and on the other case, you're switching between them on the East Coast. Which route do you think Verizon would prefer between these two? The California route, so the orange one. Why? Yeah, okay, interesting. That's a valid argument, not the one. So the proposed answer was Verizon would prefer it because you're using your own router. So you're assuming Verizon would like to have control over the part there. In reality, Verizon would like the other way because it uses less of its bandwidth, which is an expensive commodity. Right? So reasonable argument, I was going the other way. So let's say that Verizon likes the green path. Okay. Because in this case, I'm saving my bandwidth. There's another reason. Let's go with that. How would Verizon try to influence the way traffic enters their network? So Verizon is advertising Princeton's prefix to AT&T. And somehow Verizon would like to tell AT&T, hey, I would prefer it if you send me traffic to Princeton over this router that's on the East Coast. Okay? So I need some addition. Nothing in what I've told you so far would work. That we don't have anything in the protocol that would allow Verizon to implement this. And so the third attribute is an attribute that is designed to help autonomous systems influence how traffic enters their network. It's an attribute called MED, or multi-exit discriminator, and we're going to use it when ASs, typically the way it's used when ASs have two or more links between them. And the idea is to try and tell the other autonomous system how close a prefix is to the link over which it's being advertised. Okay, so let's go back to that picture here. We had, in this case, the AS that's announcing the prefix. This is Verizon is advertising Princeton's prefix, and it has these two links over which it's going to advertise it. One on the East Coast, one on the West Coast. The way it's going to use it is, MED as an attribute, is when it advertises the route over the East Coast, it's going to say, and again, the exact values don't matter, it's going to say, here's the prefix, here's the AS path. This advertisement has a MED field of, let's say, 10. Okay. And when it does it on the West Coast, it's going to give it a MED field that's higher, let's say 50. Okay, so if you think of these as costs, like our least cost routing, it's kind of trying to say the link on the East Coast has a lower cost. Does this make sense? And so now AT&T, when it hears it, has the option of saying, Verizon is trying to tell me to use this link here on the East Coast. And saving bandwidth is not the only reason Verizon might do this. Let's say AT&T had, instead of a customer that was Berkeley on the West Coast, let's say it had NYU on the East Coast. Right? If you had no MEDs, the path from NYU to Princeton, you would have no way of knowing whether you should send it over the East Coast link or the West Coast link. But it would make so much more sense to send it over the East Coast link, right? Instead of sending it across the country and then back across the country. So MED is a way you can think of it of kind of extending our notion of least cost routing across domains. Again, it's an attribute, it's a hint. There is no reason AT&T has to adopt it. But if AT&T